transmission lines of high voltage. Many a times it is required that these lines are series compensated so that the power transfer capability is much higher. Now this is the problem. This has been observed at few locations in world, that there is SSR phenomena concerned with the windmills also, right? So researchers have paid attention to analyze the problem. The synchronous generators, when they are connected to the grid via a series compensated line, the problem was analyzed with the help of small signal, that is a linearized analysis. This tool has been proved very well and accurate. So here also that tool is useful, right? Initially we will talk about the subsynchronous oscillations and the induction generator effect, and then whatever I have planned, that we will discuss that. There are three main parts which I will be showing to you. That is the mathematical modeling of synchronous generator to study the IG effect of SSR with the help of MATLAB program and Simulink. So this synchronous generator is separately connected to the grid. Now next we will study the mathematical modeling of DFIG to study IG effect of SSR with MATLAB Simulink. So here also DFIG is separately connected to the grid, right? Then we will see the impact of connecting this DFIG, doubly fed induction generator, into the power system on the SSR, right, as far as IG effect is concerned. Yeah. So these oscillations are categorized into four parts, four categories. Low frequency oscillations, that is 0.1 to 2 hertz. When the systems are too large, for example, if you take the case of India, the western region generators and eastern region generators, when they oscillate against each other, see, they are huge masses, right? So they oscillate at a much lower frequency of the order of 0.1 to 2 hertz. Inter-area oscillations, depending on the number of generators involved, we may have inter-area oscillations in which the frequency ranges from 0.4 to 0.7 hertz. We may have interplant oscillations also, say within a region. For example, the generators of South Gujarat and generators of North Gujarat, they may oscillate against each other. So obviously the masses involved are lesser, so the frequency of oscillation is higher, 2 to 3 hertz. Another, the fourth category with which our today's talk is concerned, is the subsynchronous oscillations. So the frequency of oscillation ranges what happened? My slides are visible?
Yes, sir.
I am not able to see. I don't know why. What has happened? Okay, fine. So that this is for one power plant connected to grid through a series compensated line. So these oscillations are in the frequency of the oscillation is in the order of 10 to 50 hertz. Here there are three different subcategories: induction generator effect, torsional oscillations, torque amplification. Torsional oscillations is much talked about, commonly known as SSR, right? The SSR also induces due to induction generator effect, which we'll be discussing today. So this is the system. You can see here that synchronous generator is connected to the grid through transformer, a transmission line which is series compensated. Note here that the series capacitor is connected. Series capacitor is connected, not the variable capacitor like TCSC. It is fixed series capacitor. We all know that the purpose of connecting fixed series capacitor is to increase the power transfer capability of the given line. The erection of a new transmission line is very costly. So the cheaper option is to connect series capacitor in the line. Okay, so centrally I have placed some equations where natural frequency of oscillation expression is there, which is f0, that is a normal frequency, multiplied by square root of xc by xl, where xc is the capacitive reactance of the series capacitor and xl is the total reactance of the line, transformer, generator, etc. So that is the way it is. Normally, the fraction xc by xl is less than 1. It is less than 1. So Fn is less than Fo, right? So natural frequency of oscillation is less than Fo. When the slip S is, see, if the generator is running at the synchronous speed, then there will not be any slip, right? But when the Fn is less than Fo, the slip becomes negative, right? Now remember, this Fn is the function of Xc, okay. If you look at the equivalent circuit, Re is not shown here, but Rs plus Re together, it comprises a resistance in the circuit with respect to the terminal voltage of the generator, that is the bus A. So this circuit is to be looked at the terminal A, okay, node A. Now if the slip becomes more and more negative, Rr is not dependent on the speed of the machine, but if this S becomes more and more negative, in that case what happens is, and that value is more than Rs plus Re together, then this synchronous generator becomes self-excited and the network mode gets unstable. We will see the eigen analysis also. Just to inform you here, let's say there is series RLC circuit, right? And let's say the resonant frequency depending on the, it depends only on the parameter RLC. Let's say the resonant frequency is, let's say 20 hertz, right? Now if I give supply of 50 hertz, right, in steady state, what frequency of the current current will flow at what frequency? Any answer? Hello? I am exciting that network of which the resonant frequency is 20 hertz, but that circuit is RLC circuit is excited by a source voltage source of 50 hertz. So in steady state, the current will flow. What frequency this current will have? Am I audible, Giri sir?
Supply frequency. Yes sir. You are completely
audible. That is, yeah. But in the case of disturbance, for example, if I give a step change in the resistance, or step change in the voltage, or step change in L, or step change in C. let's say we discard LNC for that matter for simplicity. So in either of the case, step change in voltage value or step change in the resistance value, we will get a current again, right, in transient. Before transient dies out quickly due to the resistance of the circuit, what are the frequencies at which current will flow in the circuit?
Participants, you make the session interactive. Sir is asking one question. Anybody can answer.
So in steady state 50 hertz current is there. In addition to that, a 20 hertz current of which magnitude dies very quickly. That 20 hertz current will also flow, right? You can check this on MATLAB if you want. I had already checked it. So the point is that there will be summation of two currents will flow, one at the 50 hertz and other at the 20 hertz, right? Similarly, in this kind of power system also, because of the inclusion of the series capacitor, there will be some network mode frequency, right? So whenever there is a disturbance, and we know that in power system continuously some changes are occurring. So because of that, the current at the resonant frequency will always flow, initiates, right? Now due to the presence of line resistance, transformer resistance and the generator winding resistance, this transient currents at the frequency of network mode dies out quickly, right? But in some cases, as we are seeing here, that if Rs by Rs is more than Rs plus Re, so this resistance becomes negative, net resistance becomes negative, and synchronous generator in this condition becomes self-excited, right? Because the net resistance is negative and the network mode becomes unstable and sustained. Okay. Here there is a system in which generator and turbines are also shown here, turbine stages. So this system, if you look at here, there is a change here. There is no mechanical system shown here, right? So no mechanical system dynamics here. There is mechanical dynamics is also there. So this masses, exciter mass, generator mass, low pressure turbine A, low pressure turbine B, intermediate pressure turbine, high pressure turbine, etc. are running in tandem, and these masses are rotating under steady state condition at rated speed. But when there is a disturbance and the currents of subsynchronous frequency induces in the rotor winding, that causes the currents to flow in rotor winding also. See, if generator winding, they are three-phase winding displaced by 120 degree in space. When they are subjected to the three-phase balance current, a rotating magnetic field is produced, which is synchronously rotating but having constant magnitude of magnetic field. But here what happens, in the generator stator winding, the currents are flowing of transient nature and of frequency subsynchronous, right? So these currents induces a magnetic field which may be in the direction of rotation of rotor or opposite, depending on the phase sequence of the current which are induced in the generator stator winding due to the disturbance in the system, right? So this, so there is a magnetic field. This magnetic field of subsynchronous frequency induces currents in the rotor also, right? Now steady magnetic field is there and these currents are flowing in the rotor winding also. So this produces the torque of the different frequencies depending on the current of the generator winding. So this causes the torque of other frequency. And if you subsequently see, the shaft section between the two masses are elastic. This masses, the shaft are twisted according to these torques, right? And this is known as torsal interaction. So here in this figure, there will be 5 torsal modes because there are 5 sections. There are 6 masses rotating in tandem, and these 6 masses are connected by 5 shaft sections. So there are 5 torsional modes. Well, our discussion point is not on the torsal interaction, so I am not discussing in detail. We'll move further. The solution is to use PSS, but the drawback is the tuning of PSS parameters is very time consuming because one generator is not standalone, it is connected to the system, right? So you need to do a detailed study in order to tune the parameters. Very detailed, complete modeling of whole system. Not only that, the damping may not be optimal, right, during the all range of operating points of the power system. So that is the drawback, right? Other solution is to use flexible AC transmission systems like SVC, FEX and so on. Sorry, TCAC and so on. But then these devices are very costly and they can inject only quadrature voltage in case of TCSC and quadrature current in case of SVC or STATCOM. Let's see the world scenario as far as renewable energy sources is concerned. World over in 2020, the generation by coal is around 30% and by RES is 13% only. So that is really worrisome situation, right? 38% is coal based generation and it is the major cause of the greenhouse effect. Temperature is increasing of the globe. If we bifurcate this 13% among solar, wind and other, we can clearly see that the wind penetration is more than 55% and it is of the order of 564 gigawatt. This is the upper graph shows the installation of wind generation annually, right, starting from 2001 to 2016, and the lower one gives you the cumulative figures, global cumulative figures, right? In 2016 it is shown it is around 486 gigawatt, but now it is 564 gigawatt. It is expected that by 2050 that may go around 1556 gigawatt if we are increasing in a moderate way, right? So the target is rising, will rise the share of wind energy by 2050 by 35%. Yeah. So there are the different types of wind turbine. The first is the fixed wind speed wind turbine. The other is variable speed wind turbine, and the third one is fully rated converter based wind turbine generator, in which permanent magnet synchronous generator is used. Now in this case, on the rotor there is permanent magnet, so no winding. So if we need to control the machine power, torque, speed, etc., then power converters which are to be required to be used will be of the full capacity. Whereas in the second option, variable speed wind turbine generator, DFIG, doubly fed induction generator, the power converter size will be much lesser, right? From the initial fundamentals of running of the machines, operation of the machines, we know that PR is equal to S into PS. So the power converter ratings will be of the order of 2 to 6% only of the total capacity of the wind generator. Now the objective of this presentation is to simulate IG effect of SSR for power system connected with SG, that is a synchronous generator. Then we will see the IG effect of SSR for power system connected with DFIG, right? And then integration of DFIG into power system using modeling, right? That we'll see, and then we will see how we can mitigate the IG effect of SSR using RES. Yeah. So this is a system. So in this system there are 6 states: phi D, phi Q, ED, EQ, ED, VCD, VCQ. VCD and VCQ are the voltages across the series capacitor. Now D and Q components we get as a result of application of the time varying transformation. Time varying transformation. Now if you look at the right hand side, we can see that all the terms from which we can say that now it is time invariant. What I am referring is, first there are 6 equations. On the right hand side of these equations, all terms are there. If you look at the each and every term, they are time invariant terms, right? So the equations are framed in such a way that the terms or the states, the first derivative of states are expressed as a summation of the terms, right, in which all terms are time invariant. Now the beauty here is that this time invariance nature of the terms or the model, this itself is a model, right? Linearized, it is called as linearized model. The linearized model, which is time invariant, is obtained because of application of time variant model, right? If we use any time invariant transformation, then we are not in a position to get time invariant model. But because of the application of time variant transformation, like Parkes transformation, right? So we get this time invariant model. And see, the small signal analysis or the linearized analysis is done using time invariant model only. Then only you get the correct idea of the system, correct insight of the system, what is happening with different modes, right? So it is very, very crucial to understand here that the application of time variant transformation is very crucial, right? That makes our model time invariant, and then only we can study the linearized model. Fine. Now there are equations of delta ID, delta IQ, VDA, VQA, which are used to eliminate algebraic equations to make synchronous generator connected to the infinite bus. I will not go into details of how these equations are obtained and used and so on. Okay. So basically, in the compact form, in the matrix form, These 6 equations are expressed as x dot equal to ax plus bu, right? So you can see the x is a state vector in which there are 6 states. These states are xd, sorry, phi d, phi q, ed, eq, vcd, vcq, right? U, that is the input, is nothing but the EFD, right? Now you see here that I am taking 2 crucial parameters of the machine, TDO, TQO. There are 4 different sets of these parameters. In a way, I can say that if I change the machine, I will have the different sets of this TDO and TQO, right? This model is implemented in the K.R. Padyasa's book, in the chapter 10. Page is also given here for your reference so that you can use it later. And the series capacitor is taken as 35%. So I will just go to the MATLAB and run the program, right? And we will see. So we'll just remember, first we will run the first column parameters, TDO 4.3, TQO 0.85. So you have seen that I have entered XC value equal to 0.35. Now, can you see the selected eigenvalues, all of you?
I think so, sir. It is not coming.
Pardon?
MATLAB is not visible.
Yes.
Is it seen? I selected eigenvalues.
Slide is not moving, sir.
1 minute. I'll just come there.
Yes, now your window is appearing.
Now, is it visible now?
Yes, yes, sir.
Command window?
Yeah, command window and that Simulink window is coming.
Okay. So now the first column, TDO 4.3, TQO 0.85. Can you read this selected values?
Yes.
Okay. So now I will run this 4.3, 0.85. Yes. So this is what I have selected. So now I will run this program. It is asking for me the value of the XC. Okay. Can you see these selected eigenvalues?
That window is not coming, sir.
Sir, not visible, sir.
I think so. You have to change the window.
Is it now?
No. Do one thing, sir. Present entire screen, then you can change the window.
I'm doing. Is it visible now?
Yes, yes. Now it is coming.
So this eigenvalue are very, very important, right? The frequency is 141.54. Can you see here in the first column?
Yes, sir.
Minus 3.267.
Yes, 141.54.
Yeah, so this is the frequency of network mode, right? See, the system which we are simulating is which one? This one, right? There is no mechanical dynamics, right? So my point here is that this program is working very nicely, which is giving you accurate results. The same results are there in the K.R. Podias's book also, right? So someone who is doing research, first of all, has to make sure that the basic study system should give you, whenever you use modeling and you do the linearized analysis, the results given should be very much correct. So that I have made sure that yes, it is giving the correct results. Okay. Okay, fine. So now I will change the values. See, the TDO is changed to 0.43 from 4.3, right, in the second column. Okay.
Mm.
So I will again clear all my variables, clear the screen also. Now it is 0.43 instead of yeah. See, the frequency of the network mode does not change. It is still same 141.5554. But then the difference is the damping of this mode has become lesser negative. Earlier it was minus 3.27. Now it is minus 1.56. So that is the result of changing the parameters. In other way, change the different machine. Okay. Okay. Now we will run the third column. The third category of machine, 4.3.085. Can you see that the network mode has become unstable now?
Yes, sir.
Can you see that?
Yes, sir. It is a positive value. The value is plus 3.00. It seems that it is
Yes.
a unstable system.
Yes. So if this machine is there running, in that case, if any disturbance, system will go unstable. Okay. Okay. Now let's check what is the value of RE. Can you see it is here 0.02? I have highlighted it. Can you see that?
Yes.
Yeah. So now I will change it to 0.001. See what are the 4.3, 0.85. See the first column, right? The TDO, TQO parameters are that of the first column in which system was found to be stable, right? Only change which I will do that change. 4.3, 0.85. And here 0.001. Okay. Clearing of all variables. Yeah. Again the same series capacitor. Now I am highlighting the unstable network mode 141.56. Can you all see that? Selected 0.72 plus 0.72. Can you all see that?
Yes, sir.
Yeah. So now what is the comment on these 4 case studies run? See, in first 3 columns, the RE value was 0.02, which means that there are, even if there is any unstable network mode, because RE is the external resistance, that is resistance of the line. Can you see here? Can you see my presentation?
Yes, sir.
Okay. So that RE is the line resistance. Earlier it was 0.02. So that was providing damping and unstable. The network mode was not becoming unstable. But then the moment we do change it to 0.02 to 0.001, which is much lesser. So now effective damping is not been provided by RE. And as a result of that, our system, which was stable in first column with the value of RE equal to 0.02, in the fourth column it has become unstable. I hope this is clear and understood.
Yes, sir.
Okay, fine. So see, again I am writing 6 states equations which are implemented like this. I hope to this gathering I don't need to explain this. So how they are implemented in MATLAB. So I don't need to explain to this. Just I will run it. Need to do something here. Please wait for a moment.
No issue, sir. No issue.
गिरी साहब, ये अल्जेब्रिक लूप का कहाँ सेटिंग होता है इसमें?
ये प्रोग्राम में सर?
नहीं ये सिमुलिंक फाइल में
एल्जेब्रिक सिमुलिंक में मतलब आपको ब्लॉक चाहिए एल्जेब्रिक वाला?
नहीं ये I will just see what is happening. Just I will show you the message.
गो इनटू सिमुलेशन सर, ये प्रोग्राम वाली फाइल को क्लोज करके सिमुलेशन वाली फाइल में जाइए।
हाँ वो कर दिया।
एक्चुअली यहाँ नहीं दिख रहा है वो।
Yeah, it is running, I think. Yes. Let me see whether it is giving any error or not. Yeah, it has run. Fine. Chalo, very nice. It has run.
No error, na sir?
No, it has run.
Fine.
I was worried actually. Which case we have run in that case? Yeah. So this shows the unstable case, right? I hope all, it is visible to all. The waveform of terminal voltage at bus A is visible to all.
No sir, actually your this M file only visible here. That simulation is not visible. You close this window and open that again.
Yeah. Is it clear now?
Yeah, now it's coming.
Yes.
Nicely.
So we, if you remember, we had last the case which was run last was corresponding to unstable modes, right? So this is why it is, right? Now we will run the other case. That time we have made this change.
That means when we selected TD very less, then it the voltage is unstable, na?
No. At that time, the resistance of the transmission line was reduced from 0.02 to 0.001.
Yes.
Right.
Okay.
So we had reduced it by factor of 20.
Okay.
Actually, it was earlier 0.020. Now it is 0.001.
Yes.
So now it is a stable case. What we have run. Can you all see these eigenvalues? Okay, I will do it again.
Only graph is coming, sir.
Yeah, I will do that again. Why I can't select all the windows?
Actually, that will come one by one, sir. This is the limitation of this.
I should select this one, I think. Okay, can you see all the eigen and especially the network code in which we are interested? Can you see it is stable -3.267?
Yes.
Can you?
Yes, sir.
Yes, sir.
Yeah,
Yes,
fine. So now we'll run on the Simulink.
Yes.
Hello, sir. I have doubt that.
Please see now this is stable, right? Terminal voltage
Yes,
at
sir.
bus. So this is stable. Please बोलिए.
Sir, this is a model of 1.1. Na? If we model this synchronous machine into 2.2 model, then how many dampings are there? That is the modes.
How many?
How many damping modes are there if we model this synchronous machine as a 2.2 model?
See, if you ask damping mode, it is not a correct term to use. We should say how many modes are unstable, right?
Yes, sir. Yes, sir. Yes, sir.
Fine, no problem. But see, the purpose of showing here 2.2 model is not, that is a detailed model of the generator, right?
Yes,
So
sir.
that is used when such cases are required. Here, especially in this case, the mechanical system total is neglected. So this is a simple starting study. So that's the reason why I have not incorporated 2.2 model, right?
Yes, sir.
Very simple case I want to show to the faculty members so that they are understanding how the study is done, what is the impact of changing different parameters and so on. Okay,
Yes, sir. Yes, sir.
fine. Okay. We have now slides are visible. Is it?
Yes, sir. Lights are
Okay.
coming. Yes.
Yeah. So now we will look at the second study system. That is the doubly fed induction machine, right? It contains a drivetrain, induction machine, DC link capacitor between the two converters. They are known as rotor side converter and grid side converter. The operations are into three types of operations are there: subsynchronous mode, synchronous mode, and super synchronous mode. So they are concerned with the speeds of the wind 10 meter per second. If the speed is below 10 meter per second, the operation is subsynchronous mode. See, the wind speed is directly related to the speed of the induction machine, right? Of course, there is a drivetrain, right? So, depending on the ratio of the drivetrain, according to the 10 meter per second wind speed, there will be speed of the machine. So, that's the reason why I am giving you three different category of operation of DFIG. Now see here, super synchronous mode operation is shown here, which means that wind speed is more than 10 meter per second. So you can see that power is fed by the stator to the grid, as well as power is also fed by the rotor to the rotor side converter, then grid side converter, and then to the grid, right? In the subsynchronous mode of operation, part of the total power produced will be fed back to the rotor and so on. So this is how it operates. Yeah. So these are the state equations of this system. Remember, the controllers are not modeled here for simplicity, right? The the three-phase voltage at the output of the rotor side converter is set to 0, and the generator voltage, that is the terminal voltage, is known as VG0, that is the initial condition. We run normally the load flow and then we calculate it, right? All the gains of the controllers are set to 0, which means that the system is operating in the open loop. Okay. Not going to the detail of mathematics. Yeah. So this is just to help you out if there are many DFIG connected at one place, right? So if you calculate this, SK is a sleep of the one generator, right? So the equivalent sleep, sorry, apparent power is apparent power. The apparent power is calculated for the summation of all the individual apparent power. This is how we should, when we model the system, right? The X aggregate is the individual machine reactance multiplied by BK, right? BK is a parameter which is defined like this: XK divided by summation of SK is the apparent power of that particular machine, of which you want to calculate Bk, divide by the total apparent power, right? In a way, it is normalized. We can say Bk is the normalized value of the apparent power. The equivalent model variables, considering the n number of turbines, HT, HG, and KTG, are expressions of them are given here, right? So let's now run the case study on the second study system. Okay, the first system tell you that corresponding to 7 meter per second, the wind speed in PU is 0.75. So first we will run the case with 0.2 PU of the XC, and then we will run the case with 0.3 PU. As usual, I will clear all the variables, then clear the screen. Yeah. So first run the case with XC equal to 0.2 PU as we have discussed, and that is 0.75, right? Yes, I will check it out. Yeah. So yes, 0.75. You can see that especially the network mode is stable. Can you see the selected network mode? Can you all
Yes,
see the
sir.
selected? Yeah, okay. Right, and now we will run with the 0.3 P. Okay, first we will run the case, or this case particularly. This will close. Fine. Fine. So the case which we have run is stable case. Okay. Can you see that this case is stable?
Yes, sir.
Hello?
Yes, sir.
Yeah, fine. If I open any other scope, is it possible that I may observe any unstable value in that scope? So just to inform you that if there is whichever the variables which are displayed on the scope of this kind of simulating file, so if the system is unstable and you run the case unstable case, then you will see that all the scopes will show the unstable waveform. Unstable waveform means the magnitude of the waveform or the value of that variable is increasing like anything. If it is unstable in one scope, it will definitely unstable in other all scope also. But the other way, if you are running the case of a stable system, then you will see the unstable in all the stable in the all the scopes. Like for example here, I open this scope. You can see it is stable case. Another waveform, right? Okay, now I will run the unstable case. Here screen. Now I run the same file again. 0.3 pu, 0.75 pu. Yeah. So can you see this network mode has been unstable selected. Okay, fine. Now I'll run that case. Yeah. Here I have changed at 5 seconds. I have changed a step change I have given. So that's the reason why it is showing again stable. Otherwise, till 5 seconds it is showing unstable. Okay. So let's change now only the spin speed and see the result. Now it is 0.95 pu. Earlier it was unstable with the x equal to 0.3. So let us take that case only. But wind speed higher. So can you see that now network mode has become stable? Now the question is why this network mode has become stable? Sleep has reduced, right? Wind speed is increased from 7 meter to 9 meter or from 7.5 pu to 9.5 pu, 0.95 pu. So value of the RR by S has reduced. So RS plus RE is now more than RS RR by RS. So that's the reason why our network mode has become stable. Let's see whether it is in reality or not. It is stable, right? Dear all, just I want to draw your attention to one fact, that this Simulink model is the detailed model, right? It covers every modeling aspect. It can, right? It depends on how you have implemented the equations. Well, I will not run the third case because of the shortage of time. Another third system. So this is how you can model the controllers for the rotor side converter and for the grid side converter. Okay, you just have to use these variables and implement the equations. Okay, in Simulink as well as in the modeling file. They are the detailed equations with controller. Not go into the detail of that. Now the twisting comes here. See, there is a synchronous generator connected to the grid through series compensated line, which has the mechanical system also. So modeling requires mechanical system modeling also. Then DFIG connected to that system at bus A, right? Now we want to study that what is the effect of DFIG on the induction generator effect, right? The DFIG converter controllers are ignored in open loop system, just for simplicity again. Converter switch, of course they are not, controllers are not there, right? So converter switching dynamics were not considered because the switching is at much higher frequency than the 50 Hz, so it's not likely to affect. And series compensation was using fixed series capacitor only. These are the detailed equations which I will not look into. Yes. Again, see, the series capacitor compensation is 0.35 pu only. So this first column here, can you see my arrow?
Yes, sir.
Yeah, okay. So if you have seen that with 0.85 TQO the system was stable, but with the 0.085 TQO the system was unstable with synchronous generator only, right? Now with this TDO and TQO 4.3 and 0.085 and wind speed 0.75, right? Again, just I would like to draw your attention here. Yeah, can you see that we have in the first column we have increased the series compensation from 0.2 to 0.3 pu and system has become unstable. But here with the inclusion of this DFIG, the system has become stable, right? Another case, if we compare synchronous generator only with the reduced transmission line resistance, the system was unstable. It was plus 0.72. The real part of the network mode eigenvalue was 0.72 plus. Now with the combined system with the IGE effect, that now it is become stable, right? Can you see that? So in conclusion, I can say that if we augment our system like this, we can say that because of the DFIG inclusion in the system, the overall system which was unstable has become stable. So conclusion is what? That in a proper way, if we connect the renewable energy source, it can help to stabilize our SSR modes of the existing system. I hope the point is clear. Here also, you know that this were the eigenvalues in which with 42% of compensation, the eigenvalue of the network mode has positive real part, means unstable mode. But with the inclusion of DFIG, that mode has become again stable and the system is stable. So this is the reason why this happens actually. If you do this kind of analysis, you will see that the resistance RE1 plays important role, right? Basically, if this DFIG is not connected, RS plus RE should be more than RR by RS. But when we introduce this to be connected bus A, this RE1 value of the RE1 plays role, right? And system becomes stable. Any question?
Participants, you can ask directly to sir.
Sir, I have doubt.
Yes.
This analysis is done in a first benchmark model, no?
No, not first benchmark model. No, it is another that system. It is not FBM. If you see my presentation, I have never mentioned FBM. Your coach?
So the written is that FBM analysis.
Where? No, it is not FBM. It is not FBM. Anyway, it doesn't make any difference. My intention is to show you that with the penetration of DFIG into the existing system, we can have stable SSR modes. That is what my main purpose to convey. I know
Okay, sir.
actually
Okay.
the work which I have presented is one of my PhD student, so I know very well it is not FBM.
Any other participants? If you have any doubt, you can ask. I hope so. Things are very much clear. Sir has presented everything in very transparent and lucid manner, and we all have enlightened by this presentation. And we are very much entire team. Actually, sir is also part of the organizing team. But still, I want to say thank you very much, sir, because this
No,
session
not
was
required. Giri sir, it is not required.
actually, sir, due to sudden change in the schedule, you accepted in a very short time. That's why I'm very much thankful to you.
Actually, what happened in the afternoon when I checked whether my MATLAB is running all the Simulink file and so on, so that when I tried to run it, they were giving me errors. So I was really worried that what I will show to the participant. So that's why I had joined late.
No issue,
And
sir. Actually, I was knowing there may be some technical issue. Otherwise, sir is very punctual about his timings. And despite from your busy schedule, and today was the holiday, you joined, sir. You have motivated to all of us. You have guided us in this domain of research. How to integrate DFIG system from the existing grid and how to obtain the stable modes through MATLAB simulations, through programming codes. You have shown a lot of things, and I hope so participants have enjoyed the session. Still, I am giving few minutes to the participant. If you want to ask anything to Dr. Joshi sir, you can ask, please. Any participant?
so my basic point was to convey that RES integrations actually solve the problem of SSR if we carefully select the size of the
Parameters.
machine and parameters of the machine. So that is
Yes,
the
yes.
main point.
Yes, sir. Actually, things were very much. Actually, when you were showing the simulations, things were very much transparent and clear. Actually, you have shown a lot of things. You changed the parameters. You changed the value of TD. You changed the value of series resistance, and you have shown how the system is becoming stable and how it is becoming unstable. It was very nice experience from this session, sir. And once again, we are very much thankful to you for taking the last moment change in the schedule because this session was supposed to be taken by Fernandez sir, IIT Bombay, but sir's schedule was today somewhere he was very busy, and that session will be taken in the Thursday morning, and the sir's session was Thursday in between, that means middle slot, but today sir has taken, and really it was very much helpful to us. Thank you very much, sir. Thank you.
I hope participants have enjoyed and understood
Yes,
some
yes, sir.
important.
Personally, I enjoyed.
They will tell me in feedback rather.
Yes, yes, sir.
Thank you.
Actually,
Thank you for.
last time your feedback was very nice, sir, at the Atal portal. I read everything.
Oh,
Last in
I'm lucky.
in previous FDP also because feedback system here we have not provided because feedback is directly taken by Atal portal. That's why we are not taking separate feedback. But
Feedback is okay. Feedback is okay, but faculty should understand what I wanted to convey. That is the main point. Feedback is
yes, yes,
negative.
sir.
That is not a problem for me. They should
No.
understand.
Yes, yes, yes.
So thank you,
And
sir. Thank you for listening me, all participants. Thanks to you all, and especially I have joined very late, almost half an hour. So I'm sorry for that due to unavoidable circumstances that has happened. But finally, I could deliver in the manner in which I wanted.
Yes, sir. Actually, you have given theoretical understanding, modeling, as well as simulation. All three things were incorporated in your presentation, sir. That was a very nice presentation, actually.
Yeah, okay. Thank you. Goodbye to all.
Thank you, sir. Thank you.
Yeah, goodbye to
Now,
all.
participants. Yeah.
Any participant want to ask question?
Participants, still sir is connected. If you want to interact, you can turn on your camera as well. Still, we have few minutes left. Actually, we will close our session at 5:45. You can interact with sir. Otherwise, we will leave and we will connect again at 10:30 tomorrow. Actually, this was the last session, sir. After 6 hours
Yeah.
online session.
Just to the participant who are asking regarding FBM. See, the system looks like FBM, but the parameters were not of the FBM.
Sir, this is very true. But when we study about the self-synchronous resonance, we will also take on the FBM as well as first benchmark and second benchmark model also. That's why I am asking regarding with this.
Are you asking something or you are stating only?
No, I am stating only, sir. We will, when we study with the sub-synchronous resonance, we will also take FBM as well as first benchmark and second benchmark model also. That's why I am asking, sir.
Correct. So, see, especially FBM is devised for study of torsional interactions. Here in my study, the interest is not based on the torsional interaction, it is on the IgE. So that's the reason why FBM is not taken as a study system. I hope it
Yes,
is
sir.
clear.
Yes, sir. It is clear, sir.
If your interest of the study is on torsional interactions, then
Yes, sir.
FBM is the designed study system by IEEE itself. So you should go
Yes,
for
sir.
FBM only if you are interested in torsional interactions.
Yes, sir. Yes, sir.
Any other participant?
It is very informative session, and the machine modeling is a very quite interesting topic regarding with the modeling of the power system. So it is very informative and very valuable session, sir.
Actually, today, just I would like to add one line. Today, sir has taken a complete package: simulation, mathematical modeling, and you can say system parameter change, everything. What he has shown. That was very much interesting. Personally, I learned a lot of things from this session, and I hope so the same from the all participants. They have learned something new from this session. This was very wonderful session. Still, I am inviting some participants to interact with sir. It is very nice time to meet at this platform. Anybody from the power system domain, you can interact. Sir is one giant fellow of the Gujarat state in the power system domain.
I am not a giant fellow, sir. It is not so.
सर ये आप बोल रहे हैं लेकिन हमारे लिए तो आप हैं.
इतना भी नहीं हूँ. Thank you, but आपका आभार. लेकिन if faculty wants to answer, if I know, I will answer.
Actually, I was your student, sir. I know how you are a teacher. As a teacher, I was your student under MTech, and you taught us. I know your quality of teaching. Personally, I would like to inform all my participants. I was a student during my ME. I taught some subjects like power system analysis, control under sir, and sir was the best rated teacher at our time.
Thank you. Any question rather than my only praises? I would like to interact with faculty members.
Yes, sir. Participants from Gujarat state, please ask something. Interact, sir.
How many participants there in from Gujarat in this FDP?
Actually, from the government system, there are 6 only.
Okay.
But from some private institutions, almost 20-21 participants are there.
Sundaram Pandya wants to communicate.
Yes, Sundaram.
Yes, sir, this is Sundaram Pandya from KJ Bharuch, SKJP Bharuch, and I have the question regarding the FBM. I already asked this question and I got the proper answer, sir. I'm basically faculty of SKJP Bharuch.
Okay, fine. So you are just introducing yourself.
No, sir. No, not at all, sir.
Asking any question, then go for it. Ask the question.
No, sir. Just you ask that how many candidates are from Gujarat. That's why I'm raised my hand, sir.
Okay. Thank you.
Okay.
Thank you.
Any other participants? Any participants can ask.
Okay, चलिए.
Yes, sir. Now we will wind up the session.
सबको थोड़ा.
Yes, sir.
Rest चाहिए सबको.
जी. And I hope so. All 3 sessions were wonderful sessions. Participants have enjoyed all 3 sessions, and we will provide the PPTs as well. And I would request sir also to provide the PPT of this session so that we can share with the participant. Because at the last of this program, we will arrange one quiz, and the question of the quiz may be asked from the whatever the contents has been covered, and you all are expected to read all those contents. So now we will leave the session, and we will meet once again for the third day at 10:30. Before 10:30 you join, please, because we will start our session sharp at 10:30. First session will start tomorrow 10:30. That is my session, and tomorrow there are 2 more speakers. One is based on control system, Professor Dipankar Deo from IIT Ram, and one is from NIT Kurukshetra, Dr. Ashwini Kumar sir, Professor and Head, Electrical Engineering. So you will enjoy, I hope so, you will enjoy all the sessions. We have completed almost 6 sessions, and all were wonderful. The speakers were so expert in their domain, so much expert in their domain. We have a pool of experts who are so good in so expertise in their domain, and our motto in this FDP is the same: to provide best content and quality to all of you. Thank you very much for joining and patient listening throughout the day. Thank you very much for your cooperation. I am monitoring the attendance as well. You all are joining in full strength. This time we are having less participants as compared to previous FDP, but most of the participants are regularly joining and staying till the end of the session. We are very much thankful. Government Engineering College Bharuch is very much thankful, and particularly for this session, entire organizing team thankful to Dr. Joshi sir for taking the last moment change of this FDP. Thank you very much, sir. Now we will depart. Thank you, sir. Namaskar. Now can we leave, sir? Kindly allow us to leave.